let's now turn to the final and trickiest operation, deleting items out of our set. So it turns out, and I'm just going to spoil the two easy cases, that there are three cases. The first is that the key that we want to delete has no children. The second is that it has one child. The third is that it has two children. By breaking it down thus, we can save ourselves some work. So let's start with the case where the deletion key has no children. Like I say, let's delete glut. So in this case, we will simply sever the parent's link. We take it away. And then what happens to the glut node? Well, it gets taken away by the garbage collector. Goodbye. Okay. So that's all we need to do to delete an item with no children. We just simply get rid of it. All right. How about deleting a key with only one child? What does this look like? Well, remember, our goal is to maintain the binary search tree property. And what we know is that whatever, in this case, if we're deleting flat, whatever its child is, it is definitely larger than my parent. Because my parent, I'm the right child of dog in this case. So what that means is it's totally safe to say that instead of pointing dog at flat, I'm just going to point my parent at my child. Okay, so if I get deleted, I point my parent at my child. And in this case, flat will get garbage collected along with its instance variables. And remember that one of those instance variables will be the address of elf. So the garbage collector in this case, it does not care that flat is pointing at elf, that it still has like a thing it cares about in the world. Too bad, you're gone. Nobody's pointing at you, so you gotta go away. So in this case, the code's a little more sophisticated than what we might have gotten out of our basic case with no children, but I'm actually not going to show it to you because it's just a little arduous, and I'll leave it as an exercise in the lab for those of you who want to do it. The key point here, though, is the concept here. We can take whoever my parent was, and we can point that parent at my child if I'm getting deleted. You might say, does that mean we need some kind of pointer back up to my parent so I know how to set their value? And it turns out there's a clever way to write this code recursively so that it is not necessary to have pointers back up, but I will leave that as an exercise for those of you who are curious. All right. So this brings us to the final and most interesting case, which is deleting a node which has two children. So I'm actually going to let you try and figure this out. I want you to try and delete K. Do it however you want, but do not Google it, because I'm gonna give you some hints if you can't figure it out. Okay, so just try and delete K. Pause this video and really try this. I think it's a pretty interesting exercise. Okay, so I would have you walk me through your approach, but I'm not going to. But if you come to live lecture sometime, then you can see what somebody else suggests and we can try it out. So what I'm going to do instead is give you a hint. Okay. So let's look at this example, back to what we had before. Let's say we wanted to delete dog. Well, I'm going to note we need a new root node. So any node that has two children, something's going to need to replace that node. And that new node must be bigger than everything in the left subtree, and it must be smaller than everything in the right subtree. So question for you, would bag work? Could I move bag up here? And the answer is no. I couldn't just take bag and put it in the root, because then alf, that would be fine on the left, but cat would not be okay. So like this stuff over here, if I move bag up, then cat is kind of in a weird spot. And then like it seems like there's a whole cascade of different changes I need. So if I try and make bag the new root, it's going to be complicated. So we want to be lazy. And this is a very important idea when it comes to algorithm design, is that maybe one of the first things you might try is let's do the laziest thing. Like if I move bag up, then I got more problems to think about. So what I want you to do now is think, well, what items in this tree might actually be safe to move into the root? Okay, what could I pick here so if I move it into the root, it's in good shape? So it turns out that cat and elf would both be good choices. If I take cat and bring it up to the root, well then everything on the left is smaller than cat, and everything on the right is larger than cat. Likewise on the right, if I brought elf up, well everything on the left, elf and bag and cat, would all be smaller than elf, and flat, glut, and eyes would all be larger than elf. So either of these two would be great choices. What's special about them? Well, it's that cat is the predecessor of the deleted item, and elf is the successor. What do I mean by that? Well, by predecessor, I mean the largest item that is smaller than the key, or than the item, and then the successor is the smallest thing that is larger. Okay. Now, what's kind of cool about this is that to do this, what you can do is like, well, how can I just move cat? Well, what I could do is just delete it and then replace the word dog with cat. Now, you might be worried that if I pick the successor or the predecessor and just try and delete it and move its key into the place of the deleted item, maybe it also has two children. Then it gets complicated, but it won't, because the predecessor and the successor, they can never have two children. Okay? The deletion is guaranteed to be either case 1, the predecessor has no child, or case 2, it has one child. And the reason is that if it had two children, then it couldn't be the predecessor or the successor. So that's a lot of reasoning out loud, but hopefully it's pretty clear. Like the short version is, if I want to delete an item with two children, I pick either the predecessor or the successor, I delete it, and I know that it's safe because it doesn't have, it only has 0 or 1 children, and that's very simple to deal with. And then I replace the root node with whatever we just deleted from down below. And this strategy is sometimes known as Hibbard deletion. And I think it's the nicest way to delete from a binary search tree, but there are many other algorithms you can try. Okay, now to test and see if that kind of long-winded explanation made sense, let's try and figure out how to delete k. So I'll give you a hint. It involves predecessors or successors. Okay, so it turns out the predecessor of k is g, and the successor is m. So here, you could pick either of these. Either of them will be perfectly fine, but I will pick g because it's a little harder. So to do this, I need to delete g. So if I delete g, that means e is going to point at f, and then k will be replaced by g. Okay, so basically g goes away, goes into the root, and we have f below. And that's it. That's the whole deletion algorithm. So it's very clever, but I think pretty cool. All right. So that's it for our search, insertion, and deletion operations. And so we'll wrap up in the next video and be on our way.